Hey, what's going on YouTube? How's it going? Not sure how many people we're going to have today, but today is our first ever discussion group, hobbyist discussion group for basic mathematics by Serge Lang. The stream replay will be available for anybody who wants to watch after the fact, for people who couldn't join live. And the idea is that this will be the paid course, I suppose. My initial thought was that it would be a high ticket, expensive, small group Zoom discussion. But we've had so many nice, positive emails, and so many people want to join to do these discussion groups that I thought, well, one way that we could run this is that I run another live stream. And this one is a larger group, but it's still a paid larger group. So it's $5 a month at the moment, the hobbyist tier membership, and we'll run these weekly, I believe. If there's enough demand, I could start a secondary discussion group to accommodate for time zones. But right now, it's looking like Saturdays 1 p.m. Eastern is the best time. So right now is 1 p.m. Eastern. I think that's just like a little late for India, and it's fairly good for the US. So, it's a decent time. We do still have the small group Zoom discussion session where everybody's on Zoom and talking together in real time together. So both options are available. Let's just jump into it. If anybody is watching the VOD after the fact, hello, nice to meet you. Leave a comment in the comment section. I would love to meet other fellow hobbyists. So Lang discussion number 1. Today is, let's go ahead and switch to the iPad. This one? Yeah, Lang discussion number 1. I see we have one person in the chat, actually, or one person viewing. Hello, nice to meet you. Not sure if that's me. That might be my own account somehow. But today, in any case, is July 18th. Is that correct? July 18th, 2026. I think so far we've worked and done videos from section 1 and section 2. Section 1 is on the integers, and there's no problems. Section 2 is rules for addition. I think that I will just work as many problems, maybe all of the problems today, so that people can get some solutions for those who want to be working problems on your own. Hey, Arlene, I'm here as a chat person. Nice to meet you. Nice to meet you, Arlene. Thank you for tuning in. I'll leave it up to you. What do you think? Do we want the background music and the Hawaii video? I think it's cleaner to not have those elements today, right? Maybe I just turn off the background music and turn off the other stuff. I think it's probably simpler to just keep it clean today. But you let me know if you like the vacation footage. I could have it. So Arlene, like, if you have any questions or thoughts, like, I'm here to take questions. I am here primarily for you. This is your time. If you want to ask any questions, give feedback on the videos, how they're going, or if there's a specific problem that you're stuck on, maybe, then I'd be happy to work anything in particular. This is kind of like office hours. One approach is just to do all of the problems. We could do that as well. So justify each step using commutativity and associativity in proving the following identities. Another way to frame that is prove the following with commutativity and associativity. A plus B plus C plus D equals A plus D plus B plus C. Okay, so here we have a couple of proofs, and I worked this one in a video earlier. So proof one, use associativity and commutativity one step at a time. We show that the left-hand side can be rewritten as the right-hand side. So we will assume one of the two sides of the identity, in this case the left-hand side, and we continue rewriting it until it equals the right-hand side. And to see an example of this, it becomes fairly tedious if we do it one step at a time, but it but it's helpful to do it once, I think, to do it this way. So we can rewrite C and D. We can swap the order of C plus D here, and we justify with using commutativity. And now this step is kind of crazy to think about. I want to zoom in literally and try to understand it. The next step, we use associativity. What am I doing exactly? We have three numbers. I'm treating L as A plus B, this sum. L, M is D, and N is C. And notice that L plus M plus N is, we can regroup parentheses, L plus M plus N. Or you could use X, Y, and Z. I like L, M, and N to mean that they're integers. X, Y, and Z often mean that they're like real numbers or something, but I like renaming and substituting with L, M, and N. Or we could rewrite saying N is A plus B, but the important thing is I want to see how I can move the parentheses on the right to the left, which is associativity. So this set of parentheses that set of parentheses I rewrote here in yellow on the next line. So that's why I can do that by associativity, and you do this one step at a time, and it takes something like 10 lines, and then you end up rewriting to the right-hand side, and then you're done. I did this in... This approach I did in episode 2, I believe. I think, or maybe it was episode 1. I think this was episode 1, actually. Yeah. Pretty confident. That was episode 1. First off, any question or any thoughts, any feedback about how the videos are going so far from you all? Like... let's see. I want to start a poll. You can vote anonymously, everybody, if you want to. The options right now are great, okay, and could be better. All right. So this is one proof, and this is an approach, and I stepped through. They're okay. Thank you. Thank you. Any kind of suggestions, I'm all ears. I would love to hear if you want to suggest things that you think could be better. I would appreciate that, but no pressure. Hey, what's up, Tao family? Are you watching all of my videos with your whole family? That would make me so happy. Thank you. I appreciate that. Proof 2. Okay, so we have one vote that says great, and I assume Arlene will vote okay. That's not bad. I'll take that. I'll take that. Proof 2. This is also a valid approach as well on this. According to Lang, anytime that you have all additions, if you only have additions, no way, you're trying to get your 4th grade son involved. That's cool because I think that for a motivated, smart 4th grader, they could learn this stuff with us. It's, it'll get harder, but we're still doing math that we did in 4th grade. We're just using letters instead. I think it's not a bad idea. And I mentioned this. You should try these with real numbers, with actual numbers. Like 1 plus 2 plus 3 plus 4 is 3 plus 7 is 10, right? So this one is 10. 1 plus 4 plus 2 plus 3. I like to use 1, 2, 3, and 4 where I can, because then I can remember, oh, D was the 4th one, B was the 2nd, C was the 3rd. 1 plus 4 is 5, 2 plus 3 is 5. So both of them, both approaches, even though we added differently, they still add up to 10. And that's not obvious. And in later math, higher math classes, you don't always have a commutativity. You don't even always have associativity, which is cool. So this is a level of formalism that we're not used to always doing, but it's fun. It creates games. Okay, so by Lang, because of the associativity of addition, if you have an equation or an identity that only has addition, there's no need to write any of the parentheses. And again, we can just say by associativity. And in particular, you can see a remark on page 9. On page 9, he makes a note that because A plus B plus C, we can regroup parentheses like this. This is a math fact. Therefore, those also equal A plus B plus C. There's no need to write parentheses if it's only addition. So it's like we also have in this equality that it's the same thing as A plus B plus C. Okay, cool. Any questions? I'm going to keep moving on, but I'm here for you all. If you have questions, if you want me to slow down, speed up, work a different exercise next, let me know. So by associativity, we don't need to write the parentheses if it's all additions. And then by commutativity, we can rearrange A plus D plus B plus C. I rearranged by commutativity multiple times. I did it multiple times, but just by using commutativity again and again, we're used to this idea that you can rearrange an addition in whatever order you want. And that's just like Gauss's proof. Remember in episode 1, Gauss proved that 1 plus 2 plus 3 plus ... 99 plus 100. Another way to reframe this is that you can add 1 from here and 1 from here, and then 2 and 99, 3 and 98, etc., until you get, I guess, 49 and 51, and then 50 at the end. But yeah, this is using commutativity multiple times. You can move and rearrange addition in any order you want. So in this, that's why I can move D over here, and I move C over, and I move B over as well. So yeah, you can rearrange additions, and now we can add parentheses back and add in specific orders, again, by associativity. And then, therefore, we are done. This is the right-hand side. So we get to draw the cute little square. So this is a much shorter proof. It's much shorter. It only took 3 lines, whereas this one, I forget how many, but it was something like 10 lines. So why did I pick this more complicated one, which is maybe a little overwhelming or something in episode 1? I think it's very instructive to see one step at a time, using each of these math tools one at a time, how you get to the right-hand side. But once you are comfortable with the fact that that is true and how that using commutativity again and again works, then you're allowed to just do it multiple times. Like in the first line, we dropped 2 sets of parentheses. We dropped the first parentheses, then we dropped the second set of parentheses. So I'm using associativity twice. And then in the next line, I'm using commutativity probably something like 5 times or something, because you need to swap D and C, D and B, D and C. Well, I guess just twice. Yeah, D and C, and then D and B. Yeah, so this is 2 associativities, 2 commutativities, and then 2 associativities. If you look in the back of the book, I think that this is exactly the proof that Lang wrote, though. So we should develop some comfort and facility with seeing multiple steps applied in a row. And neither proof is really better than the other, I feel. It depends on the audience. It depends on your intent in writing the proof. And this is where there's some like real artistry that, like math as an art with a subjective nature. Like, which of these 2 proofs is better? This one kind of skips some details. But it's much shorter. It's much more elegant, clean. Yeah, this is exactly A plus B by associativity. Oh no, he does 2 commutativity moves. Yeah, he shows 2 commutativity moves separately, so it's even in between the 2 options. Let me write exactly his proof in the back of the book. So I can swap C and D once, and then I can swap B and D in the next line, and then add back parentheses with associativity. Okay? Thank you. Any questions? Anybody want to see Luna? I kind of want to go get Luna. Be right back, if that's okay with you all. It's nice to meet you all. We could, while this group is still small, if people want to hop on Zoom, I'm happy to hop on Zoom, but if this group were to grow larger, then I don't want to make a promise that this is always like a Zoom session. There's a separate Zoom small group that's more expensive, and it's like a tight-knit, really small thing. But then so many people have emailed me and asked to join the weekend class that I thought that maybe we could do it with a live stream like this. And then the live stream is recorded, and you can always watch the video afterward and things like that. So any general ideas, feedback, requests for how the channel is going, I'm all ears. This is also kind of like a brainstorming session. Okay. I missed your explanation before on how you can remove the parentheses in step 1. Awesome. Yeah. Let me explain that a bit more. Let's see. Thank you for asking. So I do want to insist that if we want to make good progress on this book, everybody should find the book. If we're in this small session here, you can just Google basic mathematics Lang PDF and you'll find it. I love having a paper copy, so I highly recommend getting a paper copy if you can, but just no matter what, I want people to also be reading the sections, because otherwise it would just take too much time and not be very effective to just rewrite everything in the book. And then I feel a little more concerned about copyright and things like that, if I just rewrite all of the book. But anyways, on page 8, I want to refer to page numbers at times. On page 8, he says that, observe that addition works like this. That we do have, that we have associativity. He says that we will not prove this in this book. We'll just take it as an assumption. It depends on what foundations, whether or not you even can prove these. A lot of times you just assume this. And then on page 9, he says, in light of this, because the two are equal, and it doesn't matter whether you add the first two numbers first and then the third, or the second and third numbers and then add that to the first. In light of this, it is unnecessary to use parentheses. And seriously, Lang is famous for saying that some things are obvious and they're not obvious at all. So if this still isn't clear, that is totally okay. Lang is famous for that, for saying oh, this step is obvious, and it's just not sometimes. It is unnecessary to use parentheses in such a simple context, and we write simply A plus B plus C. So if your only operation is addition, then you don't need to write parentheses because it doesn't matter what order you add numbers together. That is important. An example that is not unassociative is subtraction, right? Subtraction is not commutative. You can't, like 1 minus 2 is not the same thing as 2 minus 1, and 1 minus 2 minus 3 is not the same as 1 minus 2 minus 3. Subtraction is not commutative, subtraction is not associative, so you have to write the parentheses if you have two subtractions. Otherwise, it's not clear which order you want them in. To clarify, the left-hand side here is -1, the right-hand side here is +1. The left-hand side here is 1 minus -1, which is +2. And then on the right-hand side, 1 minus 2 is -1, -1 minus 3 is -4, right? So subtraction, multiple subtractions need parentheses. Multiple additions don't need parentheses. So if we wanted to make that the step like even more clear here in our problem, which I really like I like using this 2 times in a row. Like, let n be a plus b so that our formula is now in this form, n plus c plus d. Using associativity, this fact about associativity, Lang told us that this is the same thing as n plus c plus d. We can drop one parentheses. So let's drop the second parentheses, and that would match exactly how he wrote that you can drop one parentheses. And now we can drop another set of parentheses because now we have a plus b. If n was that other stuff, then maybe m is c plus d. I'm getting like a little extra careful, and maybe it might be overwhelming or something, but I don't think it needs to be. Like, I hope that this makes sense. This math tool that he writes on page 9 tells you that you can drop one parentheses. It could either be on the left or on the right, but both of these are equal. And it tells you that you can drop one parentheses. Both of those are the same thing as a plus b plus c. But then, because you can drop one parentheses, if you have more, then you can just use this multiple times, and then if you're adding a bunch of terms together, you just use this fact to drop one parentheses at a time until this is the same as writing many additions all in a row with no parentheses. To formalize this step needs something called induction, which we're not going to cover now. We're going to just take this as intuition. These are like facts that we've learned before, and for some of us, we're relearning because it's been 40 years for some people. Like one of the people in my Zoom session just now was like, I haven't done this math in 45 years. I was like, that's so cool. That's awesome. Yeah, people are wonderful explanation. Thank you. I'm glad I'm glad that you followed that. Thank you. It's hard for me, in this kind of setting because I need to. It helps to, be able to see faces and things like that. But okay, well, thanks. So these are two different proofs for the same claim, and I think that you can even say commutativity in one line. Like he uses associativity twice in this one. Why not just use commutativity twice in one line as well? So here we are with the subjective nature of proofs. When do you fill in all the details? Is that helpful versus omitting some details and having a shorter argument? There's no clear answer sometimes. All right, we could work another problem next. Let me see. If you don't mind, first I want to join our favorite feline companion, teacher's assistant, the teacher's assistant, kitty cats. Be right back. Kitty cat. And water, technically, too. Let's go get the kitty cat. One sec. Need to get a pencil. Y'all. I want to introduce you to this one. Hello, Kaya. Hi, baby. Hi, baby. She hasn't shown up yet on stream, or if she has, or in the videos she hasn't shown up yet. Oh, Kaya. Look at this one. We have two cats. People don't know that yet in the videos. Meet Kaya. Her name is Kaya, and she's much more shy than Luna. She's much more shy. So this is Kaya. Hi, Kaya. Hi, baby. So here's cat number 2 reveal. We only have 2 cats. Black and white. True and false. Like mathematics. Like a beautiful mathematics book. Hi, Kaya. Come on. Look. Hey. The other kitty was white. Yes. Yes, we have both of them. We have both of our feline companions. Hi, Luna. Hi, Vivi. Okay, so let's get started with the next problem. Next problem. I think number 11 is worthwhile. I worked number 11 in the in the videos, but I'm not sure if everybody followed my explanation the first time. So I want to work it again, if that's okay. Or if anybody wants to see 12 instead, we could do that. Show that negative of a plus b plus c equals negative a plus negative b plus negative c. Again, I see two proofs on this, two options. Hi, Luna. So we mimic the proof of N5. Lang has this result in the text that negative of a plus b is negative a minus b, or negative a plus negative b, same thing. And now this exercise is just adding one extra term, just adding one extra number into it. So to show that some number is the inverse of another number, I don't know if x and y is better, but I like to show that m is negative n. We must show that n plus m equals 0. So this is actually the definition of negative numbers. They are invented numbers that when you add them to the primary number, they add to 0. So the definition of negative 1 is a number that you can add to 1 for them to equal 0. So if we can see that in this exercise, n is a plus b plus c, and then m is this thing on the right-hand side. And we show that I'm going to go ahead and use the notation. Oh, she's sleeping in my lap. Hi, Luna. Hi, baby. Hi, baby Luna. She's so cute. Remember that the definition of subtraction is adding the negative. So here this is just shorthand for negative a plus negative b plus negative c. So maybe it's more instructive to write this the way that he wrote it, and then say that this is like also known as this. That is the definition of subtraction, adding the negative number. Okay. So this is in the form of one of these goals. That's you assume the left-hand side and we rewrite it until it equals the right-hand side. And if we do that, then we're done. This is our strategy right now. Delete. A plus B plus C plus negative A plus negative B plus negative C. We assume the left-hand side, and now, again, we have all additions. Everywhere in all of these numbers are just additions. Even if they're addition of negative numbers, this negative A is a number negative A. In fact, I wish that we would use quotation marks instead sometimes, because the parentheses kind of mean something different in this place. But like negative A is a different number than A, and we haven't invented yet like multiplication. We don't know that negative A is negative 1 times A yet. In any case, we have numbers that are all added together. Like all of the operations are additions, so we can drop the parentheses by associativity. This is the same as A plus B plus C plus negative A plus negative B plus negative C. I wonder if for anybody, if the quotation marks make that more clear. Like, does that help anybody else out there understand? Does anybody else out there feel like that's somewhat nicer than parentheses around negative A? I don't know. I haven't seen it before, but now we can regroup. And I'm going to regroup and add my parentheses at the same time. So this is commutativity and associativity. So by commutativity, I rearranged them and then I added parentheses. And now the definition, what negative A means, is a number added to A. It's a number that inverts A to 0. It's a additive inverse of A. Negative B is the additive inverse of B, and negative C is the additive inverse of C. And now 0 plus 0 is 0. Thus, the left-hand side equals the right-hand side in our goal as desired. So we are done. We set up the goal here. This was our goal, was to show this line. So I like to put like a little question mark. Does this left-hand side equal the right-hand side there? Any questions on this proof before I show a simpler one? Or maybe, I don't know if it's simpler, but a little more clever maybe. Simpler once you see it. We want to show So this is, in N5, it was this fact with two terms. Now we're trying to show that this fact is true for three numbers, three terms, A, B, and C. Oops. Okay, well, Luna, oh, baby. Okay, I'm gonna keep going, unless there's any questions. But hey, look at how nice she is. Oh, she's very happy. Okay, so here we, in the book, he proves this fact, so we are allowed to use it in our proofs. We can use this tool that has already been shown before. This is a math fact, like a math result. So, negative of A plus B plus C is equal to, what I'm going to do is I'm going to group and use associativity so that now I have this in the form of x plus y, where y is this whole number, b plus c. So this was by associativity. If it were your paper and you only have pencil, not pens with different colors, you could write like by associativity. Like I'm doing that with color highlighting. Like the color highlighting often means something that I would write in pencil, like by this, by that, by commutativity. But now the next move that we'll do is applying N5 that we've already shown before, that this is negative A plus negative B plus C. I could use that or parentheses or something. I wonder if that helps or not. It looks a little confusing with multiple parentheses, but this fact in N5 said that we can distribute this negative, and now this thing gets a set of parentheses around it, and it has negative, like we add the negative sign in front of it, the additive inverse of the sum of B plus C. And now we can again use N5, that this is negative B plus negative C. Again by N5. Like I can distribute one negative sign into the sum, into a sum of two terms. I distributed that negative by N5 again, and now I can drop a layer of parentheses by associativity. And now we are done. This is exactly the right-hand side that we wanted. So this proof, which is an alternate proof, reuses the math fact that the section proved. The section showed this fact. You like it? Yeah, yeah, yeah. I mean, it's cleaner. It's like it's definitely nicer this approach because the basic core idea that you use in this proof, we're not just like repeating the same exact argument again and again. We're reusing that tool, in in this in this scenario. So like, there's a lot of work that's being employed by the fact that we've already proven this idea in N5, so we can apply it here. Cool. So that's an alternate proof, and I think that one is a little more elegant in the sense we don't need to dip all the way down to the definition of. This is like the definition of a negative number. And so in this way, in math, we can start moving away from the really atomic, ground level definitions and start moving to higher levels and higher layers of abstraction by reusing previous arguments that we've already made in the past. Cool. So really, again, this can be extended to any number of these. It's not just true for 2 or 3 additions, but also a million additions. That this will be negative A1 minus A2 minus A3 minus ... minus AN. And these would need to be done left to right, but yeah. Or you can write them with the plus the negative variance. So, and I hope that we can see that if we just reuse the previous fact, then that we've shown before, like if it's true for 2, then it's true for 3, and then if we check 4 additions, then we can use the fact that it's true for 3, and then because of the fact that it's used for 3, that is true for 3, then it's true for 2. Like, this creates this domino effect where I don't want to give the sneak peek to that, but this idea is induction, and we see it again and again. Like, because it's true for 2 terms, then it's also true for 3 terms, then it's also true for 4 terms, then it's also true for ... every number. Yeah. Okay, so that was that problem. Next, we could do the cancellation law for addition. How are we on time? Any questions? I really want to pause and offer an opportunity for questions, feedback, ideas. What do you want to see out of this course, especially out of the Saturday sessions? Because we could try to follow the book strictly and just work exercises from the book. Or I could show other things, like if y'all want to see some more enrichment examples. I don't know if I've said it here, but the structure that I think I'm landing on for the series, for the course, for everything, is 1 section per week of the book per week. Always 1 video on theory. based on Lang, really kind of summarizing the section that we're adding. So next week we'll start next week. We're going to learn about the rule. We're going to invent and learn about the rules for multiplication. Then I think I will tend to try to do one video of examples. So this can be solved exercises, or related examples from other books, other subjects, other math in general. Because there's so many cool examples that I know of that are not in Lang that I'd like to share with you all. How long is a session? These sessions will be about an hour, plus or minus a bit. I'm happy to hang out, especially this is the first one. I'm happy to hang out for another 30 minutes or so if y'all want to. So this is my idea for the series structure. One section of the book per week with one video on theory and one video with examples, and one discussion session, which is what this is for members. So I wonder if anybody has any feedback about episode 2 or episode 3. In episode 3, I showed a little more detail about the Fibonacci numbers. I gave some examples of adding other sequences, like the odd numbers. I gave a brief introduction to matrices, how we can add matrices, E, F, G, H. I showed adding Fibonacci numbers together and that's a useful exercise. But it was all addition practice. Like the idea was that one video of examples, especially how to practice some of these concepts. And it doesn't always have to be proofs. I feel strongly about this, that you can show pure math without proofs. You can show pure math without proofs. I feel pretty strongly about that. So if y'all want, I could talk a little bit more about some of these examples, or I could give a sneak peek to next week's multiplication session. In fact, I could show a really cool math fact around multiplication if y'all want. To me, this is one of the most mind-blowingly cool, fascinating facts about math that I show everybody. I show people this on the airplane. I show this, and nobody knows this one. like normal people, unless you studied math, most people don't know this thing. And I can explain it. I've explained it to kids. I've explained it to little kids who are learning multiplication for the first time. But you're on the edge of your seat now. You want to hear that one? Let's do that one. Okay, so I'm going to create 2 machines. Let's do it. This is my favorite. So please let me know how this goes because I'm very excited to show this in my video coming up. I like to explain this to kids, little kids. Okay, so I have two machines. This machine, I'll tell you what it does. It takes a number and it divides it by 2. So if I give the number 10 to machine A, what does it give you? It takes half of that number, which is 5, right? If I give the number 16 to machine A, it gives you the number 8, right? Okay, so that's our first machine. Our second machine is B. It triples a number and adds 1 to it. So if I give machine B the number 10, it will triple it and then add 1. So 10 tripled is 30 plus 1 is 31. If I gave it the number 5, 5 tripled is 15 plus 1 is 16, right? And I just check for understanding here with a kid, and then I say, okay, now I have a more complex machine. It depends on if you give it an even number or an odd number. It gives even numbers to machine A, and it gives odd numbers to machine B. So, if I give the number 3 to machine C, is 3 even or odd? 3 is odd. So, it's the same as what B does. What does B do again? It triples plus 1, and A divides by 2 again. So triple plus 1, 3 tripled is 9, plus 1 is 10. And if I give the number 10 to machine C, it takes half of even numbers. So half of 10 is 5, right? Okay, so when I'm doing this with a kid, it's on a piece of paper, and this is on one side, and just really on the fly, really intuitively, without using the word function, I've just introduced them to functions. But I'm showing somebody functions in context of a cool math fact. This is not the cool math fact. This is not the thing I'm trying to show you. This is just some stuff I need to show you first. But they just immediately get it when I write this down. I'm like, okay, if I give the number 10 to this machine, what does it return? What is half of 10? 5. And they've never had any trouble with like learning function notation that way. And then I flip to the other side and I say, okay, now what we're going to do is we're going to start with a number, 5. And we're going to keep giving the numbers to machine C. So with odd numbers, we triple and add 1. 5 tripled is 15, plus 1 is 16. With even numbers, we take half of even numbers. Half of 16 is 8, half of 8 is 4, half of 4 is 2, half of 2 is 1. And now 1 tripled plus 1 is 3 plus 1 is 4. And then we get stuck. We get stuck in a little loop for all of eternity. It just keeps going on. 4, 2, 1, 4, 2, 1, 4, 2, 1. Okay, now we're going to start with a slightly bigger number, but we're going to see it takes longer. And this one's going to be a little tougher. Even though 7 is just a little bit bigger, this one's going to be tougher. Tripled is 21, plus 1 is 22. Half of 22. Triple 11 is 33, so the next number is 34. Half of 34 is 17. Triple plus 1, this is the hardest one in this problem. But if you don't know, what you can do is you can triple 10 and triple 7 separately. And for a lot of kids, this is the first time that they've seen, yes, this is an unsolved problem. Exactly it is. So what is 30 plus 21 is 51. So plus 1 is 52. So you've seen this before. Half of 52 is 26. Half of 26 is 13. Tripled is 39. Half of 40 is 20. Half of 20 is 10. Half of 10 is 5. And now, guess what? Check this out. We've already done 5 before. So I could do that problem all over again, or I could just take a shortcut and say, hey, it ends up getting to 1, and then we get stuck in this loop, 421, 421, forever. Okay, so those were just 2 examples. What's amazing is that we think, but we don't know. We think that 421 is the only loop out there in the universe of numbers, and that every number, no matter what number you start with, it'll eventually drop down to 1 and then get stuck in that loop. And we've checked this for all numbers with like about 20 digits, like huge numbers. At that size, it becomes so complex that even supercomputers get stuck. It takes too long even for a supercomputer to do these problems, because sometimes these take a very long time, for certain numbers. So it seems like it's true, but we don't know yet how to argue that it will always be true. Because in math, even a giant number with 20 digits is just a little tiny grain of sand. It's less than a grain of sand in the universe of numbers. 10 to the 20 is like 0 in the infinity of numbers. So we think that it's true, but we don't know how to prove it. This pattern was discovered about 100 years ago. It's called the Collatz conjecture. And it sounds like Tau family has seen this one. Collatz conjecture. In math, a conjecture is a hypothesis. It's like an unsolved problem. This pattern was discovered about 100 years ago, and there's a famous mathematician that said math is not ready. Math is not ready for these types of problems. Like, it's so simple but it's also mysterious, and we don't know how we will solve this someday. So I really like explaining this to people because it's very simple, but apparently it's very hard. And it's just multiplication and division, and it's just a great way to really get good at your division at your 2 times table. Like, taking half of a number is the same as multiplying the other number by 2. It's so good at getting used to your 2 times table and your 3 times table. Really great at halving and tripling. Like, just great practice. Like, just think of a number in your head and try to do this in your head. Like 11, 34, 17, 52, 26, right? Try to do it in your head. Like, oh, what about 13? We've done that before. I think have we seen 15 yet? I don't think so. 15, 46, 23, 67, right? And then 67 tripled is going to be 180 plus 21. 201 plus 1 is 202. Half of 202 is 101. 304. 157. Or so, oh wait, no, 152. Etc. I mean, it can get hard. It can definitely get hard, but in the process, it's like a 10-minute explanation or something for a young kid. You've introduced functions. You've introduced function notation. You showed a a non-trivial piecewise function, right? In math language, we would say C of n equals piecewise A of n if n is even, or B of n if n is odd, right? C of n, C is like this like multi-part function. So we saw a tricky multi-part function, and then we came up with some sequences, and we have an arithmetic drill to practice tripling and halving. And then you get a neat story and the idea that math is not solved. There are unsolved problems in math, which is so cool, and not everybody knows that, I think. Awesome. Cool. I hope you all enjoyed that. I'll work one last example and then we'll call it a day unless there's any questions. The last one in Lang that I think is really valuable is 1-22. And it says, prove the cancellation law for addition. So this one, it's an exercise, but it's such an important, you love it. Great, thank you. I'm glad you like that. I think it's good. I think it's a good explainer. Like if you look at Wikipedia, the Collat's conjecture page looks really terrifying, but you can explain it to a kid with the right level of detail, or to a retiree. Like I've explained it to, retired people and to kids and everybody in between. And yeah, maybe I don't draw the functions as much for adults, but I still think it's valuable for anybody. Then B is C, right? So this is a math fact that we are very used to using all the time. If A plus B is the same as A plus C, then B is C. Okay, so let's do this. Suppose A plus B equals A plus C. Then negative A plus A plus B equals negative A plus A plus C. So how did I make this move in my proof? Hey, you enjoyed this. Awesome, Kyle. Thank you for tuning in today. How did I make this move? It's because I have this substitution. If these two are equal, if A plus B is the same as A plus C, then anywhere where I have A plus B in my equality, I can replace it. I can substitute A plus C instead. So that's how I'm making this step. I'm replacing A plus B with A plus C because I know that they're equal, right? And now I can use my associativity fact. Technically, if I wanted to be super annoying, I could use commutativity here. But either way, if you want to just jump right to the fact that that is 0, that's perfectly fine. And then 0 plus C, again, if we're annoying, we do that. And then C plus 0 is C. But it's perfectly okay, to not be that annoying. In this class, I am totally cool with just jumping right to negative A plus A is 0. 0 plus anything is itself QED, QT squared. Therefore, Oh, wait. Oh, wait. I didn't complete this thought. Also, negative a plus b equals negative a plus b, which equals 0 plus b, which is b. So I started with the same expression, and I ended up showing that that expression is c and that expression is b as well. Therefore, b equals c. I could rewrite this. I could refactor this a little bit if I wanted to make it a little cleaner and like one string of equalities. You can start with b. You can add a and subtract a. We know that a plus b equals a plus c. So a plus b by a oh no, this line is by commutativity. Like what I wrote is not wrong. it's just that it omits this detail. B is the same thing as b plus 0 by definition of 0. 0 is a minus a by definition of minus a. So I rewrote the 0 as a minus a, and now I used associativity and commutativity to swap a and b in this. Most importantly, commutativity. And now this is the same as a plus c plus negative a by assumption. We assumed that a plus b is the same thing as a plus c. So I could rewrite anywhere where I get a plus b in my proof, I can rewrite it with a plus c because I know that we assume that they are equal. And now, I can regroup. This is associativity and commutativity. A minus a, again, is 0. Definition of negative a. And definition of 0. If you add it to anything, it keeps the thing the same. It preserves the identity of c. C doesn't change if you add 0 to it. So definition of 0, definition of negative a. If I wanted to really show all the details, I could give a minus a is a plus negative a because that's the definition of subtraction. But yeah, you like the second proof better? It is a little nicer once you find a proof that goes in this kind of structure where it's like, this proof went like, I have fact 1, and I showed that it equals 2, and I showed that fact 1 equals 3. Therefore, fact 2 equals fact 3 or something. Like, it's like kind of like you step in the middle. It's like you start in the middle and you show the left and then you show the right. Once you find a proof like this, often you can take the same argument that you used from 1 to 2 and just go backwards and then go straight from, go around that diagram, right? How about any number divided by 0? That's a great question. You can't divide by 0. And that is, if I could try to tell you a little bit, why can't you divide by 0? We need a definition. What is division? A divided by B as an operation, compare this to the definition of subtraction. The definition of subtraction says A minus B is adding negative B. It's just notation. It's just shorthand. It's easier to write A minus B instead of A plus negative B, right? The definition of division, this is one symbol that we often mean like definition. Like, this is defined as A times B inverse, also known as A times 1 over B. Okay? Well, now I need to know what is B inverse. Definition of, here, I'll continue using B inverse. B inverse is a number such that B times B inverse equals 1. Right? So then, what would be 0 inverse? Let's just temporarily give that like a little label called X or ZI or something. I don't know. 0 inverse. Then 0 times X, we would need to be able to solve this equation. But 0x for any number is always 0 for all x. There is no solution to 0x equal 1. Therefore, there is no multiplicative inverse of 0, also known as 1 divided by 0. This doesn't exist. 0 inverse doesn't exist because you can never solve this equation. 0x equal 1 has no solutions. Because that equation has no solutions, we say that 0 inverse is undefined. It has no solution. 0 inverse is undefined, also known as any number divided by 0, division by 0. Remember that what we mean by division is a number times the multiplicative inverse. Well, we can't, there is no 0 inverse. That's undefined. So division by 0 is undefined. It just doesn't exist because there's no solutions to this equation. I wonder if, does that help? Like, I don't feel like anybody ever pointed at this equation when I was young. So 0 divided by 1 is 0. That is true. That is true. 0 divided by anything is 0. And what the reason for that is that 0 times anything is always 0. This is an important fact about 0 when we introduce multiplication. 0 times anything must be 0. I think we can prove this. I think we can prove that this is true. This is in Lang. This is fact N6 on page 14. That 0a equals 0 and 1a equals a. He doesn't prove it. He doesn't prove it, but in a higher... Ooh. At the bottom of page 15, he does, actually. Awesome. Super cool. He does prove it. And I encourage you all to read the proof on page 15. So 0 times anything is 0. Therefore, there's no solution to 0x equals 1. So then there is no multiplicative inverse of 0, which is what we mean by division by 0, multiplying by the multiplicative inverse. You can't multiply anything by 1 divided by 0. Okay, I hope that helped. We're getting kind of a little abstract, but also more clear. Like, the fact that you can't divide by 0 is a fact that we all learn and we memorize and we say a bunch, but I don't think anybody ever showed me why when I was young. So it's so related to the fact that subtraction is just, it's related, it's the inverse of addition. Division is the inverse of multiplication. In the numbers, there are only 2 operations. In the real numbers, there is addition and multiplication, and subtraction and division are just conveniences. They're just another way to write additions and another way to write multiplication. The only 2 real math operations are addition and multiplication. Subtraction is addition of a negative, and division is multiplication by the inverse. Cool. Okay, well, thank you all. I gotta run. I had a blast today. I really hope you all enjoyed this. I can share these notes somewhere and make like a paid, like, members only post or something, so I can get these to you. If you all want to join the Discord, it's a nice little group, and if you let me know, I can give you a special role and invite you to like a members only channel. Yeah. let me know if anybody wants to or plans to join the Discord, and I can get that set up now. Thank you. Sharing notes is awesome. I will do that. Yeah. I think that's really great. Cool. Okay. Well, thank you so much. I had a blast. This was fun, and it was also really great practice for me, lecturing or running like a discussion group. Take care, everybody. Hope to see you around. Feedback is a gift, as always, and see you around. See you next time. I'll be back on this time next week to run another discussion group. All right. Bye. Bye, everyone.